Today, we're talking about hidden Markov model. This is a computational approach that has been widely used in computational biology. So we will first go through what is Markov chain, and then explain what is hidden Markov model, and then we'll teach you how to use this to do some inference. In order to understand Markov chain, we first need to understand independently and identically distributed events, which are events that are not correlated with each other. Basically, the current event has no predictive power of future events. For example, the probability a couple had a boy as their first child to infer the probability of the next child being a girl is the same as the probability of having a girl in the first place. Whether the previous baby is a boy or girl doesn't matter. And supposedly you have a fair coin and you're asking, what's the probability that I'm going to use this coin to flip a head, knowing the previous flip is a head. Again, this is IID because the previous coin doesn't really matter. It's always the same probability that you will flip a head at this time. And also, if you have a dice and it's kind of a fair dice, you know that the previous dice throw is a 5. The likelihood that you are going to get a 1 is the same as the 1 by itself. And so that's IID. And in order to understand discrete Markov chain, we also need to understand what is a Markov process. And so in this process, we have distinct states, which in the previous example would be the dice having different heads or the different numbers and so on. But also we have regularly spaced discrete times, such as day 1, day 2, or the first row and the second row. And so in a Markov chain, instead of IID, where one event has no effect on the future events, in Markov chain, future states can be dependent on the current state. But depending on the level of Markov chain, it can be dependent on just the present state or one level before or 2 level before. So that will be like a first order Markov chain, second order Markov chain. But before that, it doesn't have effect. And so let's think about a very simple first order Markov chain, which means the future state only depends on the present state, one state, but not any state before, any way to get here. So to write this in an equation, it means that the probability at time t that you will get to a particular state, knowing all the previous events, we see that this is only dependent on the t-1 event. And so the t-2, t-3, all the previous events doesn't matter, but the t-1 event has some influence on the current state. And this is something called a transition probability, which is often written as AIJ, which is knowing that the t-1, you get a state I, we want to know what's the probability at time t, we will get to a state j. And so because this is a probability, all the numbers should be larger than or equal to 0. And imagine in the t state, in the t time, if there are overall X number of options, the total option together should add up to 1. And so this is the transition probability. And so in a Markov chain, we can imagine the following situation. So if we know a student has exam grade for the previous exam as a pass, and so the states could be just pass or fail. The discrete times would be exam 1, exam 2, exam 3, and so on. And imagine we have the following state transition. And so this would mean that if the student has passed exam 1, the likelihood that they will pass again will be 0.8, but the chance they will fail is 0.2. But if a student failed that first exam, their probability of passing is only 50% and failing is also 50%. You can see here, these two numbers add up to 1 and these two numbers add up to 1. So we can ask, given the student has this track record, so like in 6 exams so far on a course, they had pass, 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 fail, 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 the probability of passing the next exam is, the 7th exam being a pass, given the transition probability and all the string of events that has happened, we will say that, okay, it depends on the transition probability. And because this is a Markov chain, which only depends on the previous one exam, then we know that the previous exam is a fail. And therefore, looking at this transition probability, we know that there's a 50% chance failing again. Another example for the states, we have rain, cloudy, and sunny days. This is weather. And the discrete time is day 1, 2, 3, 4. And we have the following transition probability. If you have rainy day, there's a 40% chance it will rain again, 30% chance cloudy, and 30% sunny. If it's cloudy, 60% chance it will be cloudy again, but 20% chance rain or sunny. And if it's sunny, it's 80% sunny again and 10% each for rain and cloudy. Of course, this is a completely artificial transition matrix. But imagine we have a transition matrix like this. We can say that given at day 1, we have a sunny day, what's the probability of observing the following string of events, which is sunny, 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 rain, rain, sunny, cloudy, and sunny. And knowing that the first day is a sunny day, we just ask, what is the probability we will have a sunny day again? That's transition A33, it's 0.8. And then from second day to the third day, again, is transition A33 is again 0.8. And then from sunny to rain, it's A31 is 0.1, and then 1 to 1 or rain to rain is 0.4, and then rain to sunny again is 0.3, and then rain to cloudy is 0.1, and cloudy to sunny is 0.2. And so you can calculate that probability. So you can see if these types of transition probabilities are given, we can predict the likelihood certain string of events are going to happen. And the third example is a case where you use a coin to flip to decide to pick coins. So supposedly we have a fair coin, that's one state. Another coin is a biased coin, B. And the discrete times is, you are using a fair coin versus an unfair or biased coin. We introduced this new concept of initial probability, which is what's the likelihood that I'm gonna just use a fair coin in the first place. It's 0.4, and later, and also the initial likelihood of using a biased coin is 0.6. And also for the transition probability, we can write it as a matrix like this, but you can also imagine writing it something like this, which is if I'm already using a fair coin, the likelihood I will use a fair coin again is 0.9, or I use another coin, the bias coin, which is 0.1. But if I'm on the bias coin, 70% chance I will use the same coin, but 30% chance I'm gonna flip to the fair coin. And so now I can ask the similar question. What's the probability of fair, fair, bias, bias, fair, 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 biased? And so the difference from the previous example is that we know at time 1, the state is sunny, whereas in this case, we don't know the initial state. Therefore, we first start with what's the probability of seeing a fair coin in the first place. And we know that is 0.4. And then after that, it will be the transition probability from fair to fair, fair to bias, bias to bias, bias to fair, and so on. And you just multiply the probability. And so that's kind of how Markov chain works. After understanding IID and Markov chain, we now go to hidden Markov model. And so in this situation, you can see here is the transition probability from a fair coin and to a bias coin. And on top of that, when we're using a coin, we're making a flip, and you might get a head or a tail, and we keep track of the actual observation. This is head, head, and tail, tail, and so on. And so the underlying states are the coin that we use to get this particular coin flip, right? So the coin transition follows a Markov chain process. The probability of flipping to get a head or a tail depends on the coin you use. For example, if the fair coin is 50-50 of head and tail, but the bias coin is really different, it has a much higher probability of one side to the other, and then depending on the coin you use, the likelihood you are seeing a tail or head would be quite different. And so let's imagine the situation where the states, the coin you are using is not known. So it's kind of the coin used is under the table, you don't know. And after the coin flip, you are only told that, yes, this coin flip is a head or a tail. This is called a hidden Markov chain because the coin state is hidden from the observation. You only observe a string of head and tail. And so in the hidden Markov model, there are the following elements. We still have the number of states. In this case, we'll have fair coin versus bias coin. We still have the distinct time or distinct observations, which is here is the observation, which is the tail or head of the actual coin flip. And then we also have the initial probability of picking the first coin being a fair coin or a bias coin. We have the transition probability, which was given before. You tend to stay with the same coin, but sometimes you will flip to change to the other. And there's another parameter which is important, which is the emission probability, which is the likelihood of flipping a head or a tail given the coin you have. For example, if we have fair coin, we have 50-50 chance, but if we have a bias coin, in this case, we are 80% chance to get a head. And so these are the models that we have. And using hidden Markov model, there are many useful applications. Imagine you have stock market. You have the stock price, let's just say NASDAQ. You have the value of the NASDAQ market every day. And even though there are fluctuations from day to day, economists might call a whole period of, say, a few months as the bull market, because overall things are going up, or a bear market when things are going down, despite the individual fluctuations up and down. Similar to, like the bear and bull would be the fair coin versus bias coin, and the specific day that the stock goes up or down would be whether you get a head or tail on the coin flip, right? There are also applications using hidden Markov models such as speech recognition. So the sentence or words that are actually being spoken to, these are the hidden states that a machine would not necessarily understand, but the machine can detect or hear the sound coming out from somebody. And then it will try to guess what's the underlying words or sentences that are spoken. Also applications such as digital signal processing. So the original source might be a 0-1 signal, but it's unknown to the receiver. And the receiver actually gets a more fluctuated signal, which is, the actual signal coming is not clearly 0 to 1. It's kind of analog signal. and it's trying to guess whether the signal coming from the digital signal initially was a 0 or 1, because it knows that at every time what kind of a noise there is. There are also a lot of bioinformatics applications, but before we go to those, I want to kind of show you how hidden Markov model works. There are three basic problems in a hidden Markov model. For simplicity, we are going to use the coin flip example, but later on in the bioinformatics application section, you can see how this is being used in real problems. The three problems in hidden Markov model, the first one is, given that the parameters for the hidden Markov models are all provided, how do we compute the likelihood of a particular observation? For example, if we know there is a fair coin, bias coin, if we know the initial probability and transition probability and emission probability, can we calculate the probability of seeing a string of coin flips, such as head, tail, tail, head, 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 tail? And so for that, there are two computational procedures that can achieve this answer. But first, let's think about how we want to solve this problem. So let me remind you again, the initial probability, transition probability of this hidden Markov model. So supposedly, we know the state sequence. If the observation is this, and if we know that the coins that are used underneath each coin flip is the following, FF, bias, and so on. We can easily calculate this based on the transition probability. From a fair coin to get to a head is 50%. A fair coin to a tail is 50%. Bias coin to get a tail is 20%. And bias coin to get a head is 80%, right? So very easy, you can calculate this. If I give you another coin, like a string of coin order, which have these two coins changed, we can calculate the probability again, which will give you a different result from the path above, but it's a very easy calculation. So you can see, given each path, you can easily calculate the probability using the emission probability of the two coins. Then the question is, what is the probability of seeing this path? Let's look at the first path. In order to use this particular order of coins, we say, oh, well, first we have to pick a fair coin. So that's the initial probability of 0.4. But also we have a transition probability from a fair coin to another fair coin, from the fair to bias, bias to fair, fair to fair, fair to bias, bias to bias. And so that you check the transition probability, and you can calculate this quite easily. If now look at the second path that we're given. Again, we have to start using this bias coin. That's from the initial probability. And then after that, you just check the transition probability from one coin to the next. You can calculate this probability. And so you can see here, it's also fairly easy. Every given path has its own probability of occurring, knowing the hidden Markov model parameters. Therefore, the probability of seeing this particular coin flip order is to sum over all the possible paths. Every path has its own probability of happening, multiplied by the probability that on this path, you are going to give out this particular coin flip, right? So you can see written as this is the probability of a particular path given the hidden Markov model parameter. And with the parameter, with that particular path, what is the probability that this path will give out this particular coin flip? But you have to sum over all the possible paths, right? So you can imagine for a path with n long, so n number of events in here, and the t number of hidden states, in our case, the hidden states are fair coin and bias coin. There are 2 to the n possible paths. And so imagine if the t is high and n is also long, say stock market, you are looking at a year, there's only bear and bull market, 2 to the 365 days. It's an unfeasible calculation. That's why you need a better computational algorithm to solve this problem. And for that, we use dynamic programming. Dynamic programming is an approach that we can keep the previous subproblem solution in order to speed up the current calculation. And so in this situation, we try to keep track of all the numbers we get from the previous step, because at every time point, we have to calculate probability, and we'll show you how you can keep track of the previous step's result in order to help you with the next step of result. This way, we don't have to enumerate all the possible paths in order to calculate the final probability. So let me show you the first approach, which is called the forward procedure. Again, we have this particular coin flip, and we want to see, what is the likelihood this is going to happen. And so you initialize like this. We ask, what is the probability of seeing a head from the fair coin or biased coin? And so let's just calculate one at a time. You can see here, this is let's use this red circle here to indicate the probability of using a fair coin in order to get this head. This is calculated as, we have to pick a fair coin in the first place, which is the initial probability of picking a fair coin. And then from that fair coin, we have to emit a head from the fair coin emission probability. We can calculate the same for the other side, which is a number we keep track of in this yellow circle here. If we use a biased coin, initial probability is biased coin, and the emission probability from the biased coin to give out this head. And so that's, here, initial probability times transition probability. And you keep track these two numbers, and we call them alpha. So the alpha 1 is the probability of seeing a head using a fair coin at the first position. The alpha 1b is the probability of using bias coin to get this head in the first position. And now we look at the next step. So again, we say alpha actually is now keeping track of the probability of seeing a particular coin flip at this location, and all the numbers before, all the possible coin flip before. Let's look at this particular coin flip. At the second coin, we ask, what is the probability that we are getting this T and also the previous H if we're using a fair coin? We say, well, what are the possibilities? In the previous coin, we could use a fair coin, but transition from the fair coin to a bias coin, or we can use the bias coin and transition to a fair coin. And so, and both are possible. So we just add up their probabilities together. In this case, it would be, it would be this alpha, this yellow number stored in here, multiplied by the transition probability from a fair coin to a fair coin, plus this probability of previous coin using bias to get this head, multiplied by the transition probability from the bias coin to a fair coin. And so when we sum these together, we know that now we are on the fair coin, but also from here, we need to emit a tail using this fair coin. So we multiply this, the sum of these two numbers by the emission probability here. And we can do the same thing for this other side. What's the probability of using a biased coin in order to get a tail here and everything before? And we say, okay, well, we know that in order to get anything before, that if that previous coin was coming from a fair coin, that's the probability. We multiply by this yellow number here, the alpha number here, by the transition probability from the fair coin to the bias coin. The other option is, to come from the bias coin, and we inherit this yellow alpha number here from the bias coin here, and then transition from bias to bias coin. That's the transition probability. We sum this together, and so now we know we are using a bias coin. But using this coin, there is also a emission probability of giving out a tail from the bias coin. And so if you convert that into the probability calculation, you can see here, we inherit the previous number here, multiply by the transition probability, and sum by this number, and then multiply by the transition probability, and we sum them together, and then from the fair coin we emit the head, right? And then so on. And so you can see at every step we calculate the summation of the previous and use the results from the previous step. And now if we continue this calculation, we ask, what is the probability that in the third coin, I'm going to get a T if I use a fair coin? We say, okay, well, if you use a fair coin now, well, what's the probability that the previous coin is a fair coin? Well, if the previous coin is a fair coin, in order to get anything before that, this is the probability we already calculated. But then we have to transition from this fair coin to the fair coin. So that's multiplied by the transition probability. Alternatively, the previous coin could be a bias coin. And then we'll inherit this number, which calculates the probability of using a bias coin to get all the coin flips before, multiplied by the transition probability from a bias coin to a fair coin. And we add up these two numbers together. Now we are in a fair coin, and then we have to emit the tail from this fair coin, right? Or you can calculate the probability of emitting the same tail and everything before using the bias coin here. Again, there are two options. You either inherit this number, multiply by the transition, or you inherit in the previous coin being biased and you do the bias to bias transition. You sum them up, and then at this bias coin, you emit the tail. And so you can see here, the calculation is much easier. At every step, we trust that the previous number was calculated correctly, and we just inherit this number to help us calculate the next step, and so on. And so, yeah, same thing here, like this. And so now if you think about if the string of coin flip is very, very long, like 300 long, instead of calculating all 2 to the 300 times, 2 to the power of 300, at every step, we only just inherit the previous two numbers. And it's kind of almost linear to the path you have. Right, so it's if you have n states, n time points and t different states, it will only be n times t. So it's a much more manageable calculation, very, very fast. At the very end, if we reach the end of the 3000, we say, well, what is the final probability of observing this particular string of coin flip? Supposedly we only end at 4. You say, well, at the end, I just need to make sure that the probability of getting all the coin flips are already here, and the final coin flip I'm getting ahead, but that can come either from the fair coin or coming from the bias coin. And so I just add two numbers together and then I'm done. So you add the final two numbers, you will get the probability of that particular coin, the particular order of coin toss you observed. So that's the forward procedure. In order to answer the first problem, in addition to forward procedure, there is also another procedure called backward procedure. And so you go from the end forward, backward. And so again, here we have the coin flip. And at the very end, we're asking, so now we keep track of this yellow number and we call them beta. This can give you the probability of using this coin in order to see this particular flip, in order to see the flips after it, not including this one. It's in the very beginning, it might be a little opaque, but just bear with me. So initially, you give both of them 1. You say, well, because there's no coin flip, we're done. And so you give this first beta number 1 on both sides. But in backward procedure, at every particular coin flip, we ask, what's the probability that the coin after that is either a fair or biased. We will see how this works here. If we ask, what is the likelihood? What's the probability that I'm going to use a fair coin here in order to see the next coin flip and things after it? It will be this tail. And so if we know that this is a fair coin, there are two possibilities. One is I'm still using a fair coin here. So it's a transition from fair to fair. And then from this fair coin, I'm going to emit a tail. That's an emission probability. And then I will inherit this beta number because that will help me capture everything afterwards. And so it's, transition probability multiplied by the emission probability multiplied by the beta number you inherited. Alternatively, I can be using a fair coin here, but the next coin can be coming from the biased coin. And so that's a transition from fair to biased. And at this biased coin, I can also flip a tail, which is a transition probability of getting the tail from biased coin. And then I will inherit all the numbers calculated from this beta number, because that will help tell me, already calculated the sum of all the things after it. And so these two are kind of two paths. We add them together, and that will give me the new beta number at this location. The same thing here. If we want to calculate the probability of using a biased coin at this location in order to see the coin flip after this, which is T in here, it's a biased coin to fair coin transition, fair coin to emit a tail and inherit everything after. Or it's biased coin transition to biased coin, and this biased coin to emit this tail and inherit everything after. I add them together because both are possible in order to use a biased coin at this location. And so you can do the math, you get some probability, and then we can keep going for the next, the previous coin. And so here, again, transition from fair to fair, from fair to emit a head, and then I will inherit the beta numbers because that will calculate everything after it, using this as a fair coin to get a head and tail. Or I can go from transition from the fair coin to a biased coin, emission from a biased coin to this head, and then inherit all the coin flip after that, and so on, right? So you can do the same thing. And so at every step, I'm calculating the likelihood I'm going to use this coin, but the next coin could either be either be fair or be biased in order to get, the head and everything after it. And so again, this is a calculation you only need to do at every step, looking at the number after it, right? So again, it's a linear kind of a equation, n times t. You will be able to calculate this. And at the very, very end, it's like this. We are now here. We ask, what is the probability I'm going to use a fair coin in order to see everything after it. That is the probability. First, I have to pick the fair coin. So that's the initial probability. And then I will emit a fair coin in here, and then be, and then inherit everything. Sorry. This is coming from this location. You can imagine if you start from nothing, we first have to emit a initial probability of a fair coin. And then from that fair coin, I have to emit a head. I think I have a typo. Yeah, sorry, this is the one. From the fair coin, I have to emit a head. And then I inherit this number to get every coin flip after. Alternatively, I could initially be picking the bias coin. That's the initial probability, and then emit the head from the bias coin, and then inherit this beta number to get all the coin flips after. And I sum them up together. And that will be the end of my backward procedure. You could try this on the coin flip example. And what you should see is that both forward and backward procedure can be used to solve the first problem, which is the probability of seeing a particular string of coins that happened. And you will see that these two procedures should give you identical results. Because you either look from the front to the end, or you look from the end to the beginning, and they will give you the same result. The first hidden Markov model is to calculate the probability of a particular string of observations, knowing the parameter of the hidden Markov model. And we discussed two procedures, forward and backward procedure, and they should give you identical results. The second problem is to infer the hidden states. If I have a particular observation, a string coin flip in this case, I would like to ask, if I don't know the hidden coins, can I guess what that hidden coin is? So if I have a string of coin flip like this, HTT, HHHT, I would ask, what is the probability the first coin is fair coin, second coin is fair coin, and so on. And the solution to this, also there are two different solutions. The first is called a forward-backward procedure. And so basically, you run the forward procedure first, and you get all the alpha numbers in here. Remember what the alpha numbers mean. They tell us the probability of seeing this coin, of using this coin, in order to see all the flips now and before. So at this coin, like at this location, I'm seeing a T. What's the probability I'm using a fair coin now in order to see this tail and all the flips before? So that's you calculate all the alpha numbers here. And then we also run the backward procedure to calculate the beta numbers. And remember what the beta numbers mean, which is the probability of using this coin in order to see everything after, all the flips after. And so beta 3F is, what's the probability that I can use a fair coin now in order to see HT, the things after that, right? Whereas the alpha 3T is what's the probability of using a fair coin in order to see T, and before that T and H. And so we run the forward procedure, we run the backward procedure, we'll fill this matrix, then we can calculate this probability. The probability at this position of using a fair coin is basically alpha 3 times beta 3 in order to get this whole thing. Because if I'm using a fair coin, the alpha 3 tell me if I use fair coin, I will see everything before. And the beta 3 tell me if I use a fair coin, these are the probability of seeing everything after. Therefore, when you multiply these two numbers together, that's the probability. The third coin being a fair coin in order to see the whole thing. And so you are using the whole chain to help you make the best guess of what's happening at this third location. And that is just the probability, but you have to sum over all your other options. And what are the other options at this location? You can either use a fair coin or you can use a bias coin. The probability of at this location of to get a fair coin is the alpha 3 fair times the beta 3 fair at this location. But what if I'm using a biased coin at this location? That's your alpha 3 using bias coin and the beta 3 using bias coin. So that's the probability. And so you sum these two together as your denominator, and this is your numerator. And this is the final probability, 0.659. And at this point, whichever probability is larger than 50%, that's the probability you assign to that particular coin. So in this case, because the fair coin probability is 0.659, we'll say, oh, the third position is a fair coin. But not only you are given a prediction, you are given a confidence of the prediction. So at some positions, you might be 99% sure that this is a fair coin, but at other locations, you're only 0.51%, only 51% sure. So you have a confidence at every location as well. And so the forward to backward procedure can maximize the expected number of correctly predicted states throughout the coin flip. So imagine if you have a very, very long string of coin flip at every location, you use all the information before and all the information after, all the coin flips after and all the coin flips before in order to make your best guess of what's the coin that's used at this location. And if you use the forward backward procedure, it will maximize your expected number of states at every coin flip that's correctly predicted. And so that's one solution to the second problem. For the same problem, besides forward backward procedure, there's an alternative approach, which is called a Viterbi algorithm. You can go through this equation yourself, but we'll just show you something very simple. Again, using this example. So instead of keeping track of alpha and beta numbers, here we're using a delta number and a psi number. So the delta keep track of the maximum probability to use a fair coin or to use the particular coin in order to get to this point. The psi is a pointer to keep track of how I got here. So you can, I'll show you how to do this. So initially, the initial probability is we calculate this delta number, which is here for the delta 1 using a fair coin would be initially I have to pick the fair coin, so that's the initial probability, multiplied by the emission probability of using a fair coin to get ahead. And so these two multiply together, you'll get this delta number. And we also look at the delta for bias coin, which is you pick this coin to start with, you emit a head based on the bias coin using the emission probability. So you keep track of this delta number. And then we start to go through the Markov chain. At every point, remember for forward-backward procedure, we calculate the sum. But for Viterbi algorithm, we keep track of, we only use the maximum of the two numbers, or in this situation, we only have two paths, so you just use the bigger number. But in some situation, you might have multiple states, then we pick the maximum number to use. So, so let's say if we want to calculate the probability of, or not probability, we want to look at this delta number for the second coin being a fair coin. We say, well, if this is a fair coin, what are the chances that, there's one possibility that the previous coin was already a fair coin, and we inherit this delta number, and then transition from the fair coin to a fair coin. Alternatively, we come from the bias coin here in order to get all the coin flips before that, and we transition from the bias coin to the fair coin. And so it's this delta number multiplied by this transition probability. And at this point, instead of summing them up, we make a comparison. We check which one is the biggest. And in this case, let's just say this pass gave me a bigger number. Then my psi is a pointer to say, okay, actually, I'm adopting this particular path in order to use this fair coin. And then at this fair coin, so basically you will only use this previous delta number multiplied by this particular transition probability, and then multiplied by the emission probability from the fair coin to emit a tail. And then you keep track of this new delta number here. And same thing here, if we calculate compare the probability of getting here from the fair coin, that will be this delta number multiplied by the transition probability from fair to bias. Compare with this, if we use a bias coin here and transition from bias to bias, so this delta number multiplied by this transition probability, we again do a comparison, and we pick the bigger one and use that number to multiply by the transition probability of a bias coin to give out a tail. And the pointer here, the psi, will keep track of the path to get here. And so we do this at every step. We say, well, next one, again, we inherit this number multiplied by the transition probability and compare with if the previous coin is a bias coin, and multiply by the transition probability. We make a comparison. We basically, at every step, we always pick the winner. Instead of summing them up, we always pick the winner. And then we know at this point, from fair coin, we have to emit a tail. And alternatively, we try, not alternatively, we can also calculate the same delta parameter for the bias coin. It could come from a fair coin, or it could come from the bias coin. We pick a winner again, and at this point we emit the tail, and so on. And so this is again a Markov chain. It also uses dynamic programming because at every step we keep track of the delta number and we use it for the next calculation. And how does this terminate? So at the final termination, we just compare the two numbers at the very end, the two delta numbers at the end. And again, we pick the bigger number, or the best, the maximum number. And supposedly the bias coin give us a better delta number. Then we just backtrack. We ask, in order to use the bias coin to get this, because we know this is giving us a higher probability, then we ask, how did we get here? Well, based on the psi to keep track of our path, we know, oh, okay, in order to get here, we took this path and the previous coin is biased. And then the pointer tells us that the previous coin is fair, and then the previous coin is biased. And so we will have the path as well. And so compared to the, and so at the end, you output your prediction, which is, bias, fair, bias, biased. And this give you another solution to the second problem, which is the path. The difference between Viterbi and forward-backward procedure is that, remember we mentioned that in order to see this particular coin flip, there are a gazillion different ways you could use the coins. There's different path. Every path will have a probability of giving you this head, tail, tail, head coin flip. And Viterbi algorithm will find the path that give you the highest probability of flipping out this particular string of coins. And because at every step, you pick the winner. And at every very end, you pick the ultimate winner and you backtrack. And you make sure that, because this is the ultimate winner, at every step, again, you pick the winner. Therefore, this is the correct path that gave you the highest probability among all the paths to give out this particular coin flip. In most of the locations, you might see that the Viterbi algorithm and forward-backward algorithm give you very similar predictions, but occasionally there could be something that are slightly different. For example, sometimes the forward-backward algorithm, remember, it maximizes the overall at every state, the final states being correctly predicted, whereas Viterbi give you the path that have the highest probability. Sometimes a forward-backward algorithm might give you a path that based on your transition probability could never happen. But Viterbi algorithm will always give you a plausible path. And so most of the time you will see that they give you similar predictions, but occasionally there might be some small differences. Oops. The third problem is a lot harder. You can see here, I made it gray. I only teach you, I want to show you the intuition, but not necessarily the strict solution to this. The third question is a lot harder. Supposedly, you are given the coin flip result, but you are not given the parameters, which includes the initial probability, the transition probability, and the emission probability. Then how do we really estimate this? So to estimate the parameters as well as getting the path information, this is a little harder. There's actually not a definitive solution for this. It's no guarantee that you will get the best solution. So there are some solutions that can get you some good result, but there's no guarantee to get the global optimum. That's the Baum-Welch method, which is kind of similar to the expectation maximization approach that we discussed in transcription factor motif analysis. We randomly initialize some parameters, and based on the initialized parameters, we can run the forward-backward algorithm to estimate the path. And then we can update the parameters based on the path you estimated. So let's look at this situation. So supposedly we have a string of coin flip, and we know that there's a fair coin and a biased coin, but we don't really know how the parameters are really set up, what's their transition, and what's their emission probability. We can make some very simple guesses, right? Just, you can do this by random, but you can also just make some reasonable guesses initially. You say, oh, well, this region seemed to be fairly half-half, I'll just call it a fair coin. And this region, well, it seems like to have more head than tail, I'll just call it as bias. And this region is more fair, and another region maybe fair. And just you give it something. And based on this, we can calculate a initial probability, which is you count the total number of fair versus bias. And the ratio of that is your initial probability. So what's the total number of fair over all the coins, all the flips in here? That's your initial probability. You can also look at the transition probability in here, which is, how often in this case, I just made some initial guesses that this is a fair to fair. You can see there's another fair to fair, fair to fair, fair to fair. So you can see it happens fairly often, but there is one transition probability from fair to bias. There's then these are all counting towards the bias to bias transition. There is a bias to fair change, and then these are fair to fair transition all the way. And there is a coin flip. It's like a change of coin. There's another change of coin, and so based on this, you can make some estimate. You can calculate what is the transition probability. And then based on this, you ask, okay, if I look at all the fair coins I have, what is the, I can calculate precisely what's the probability I'm using a fair coin to get a tail versus head. And you can calculate also under all the bias coins, what is the probability of seeing a head and the tail. And so now see, based on the initial guess, you can estimate the parameters. But then knowing those parameters and knowing the coin flip again, so now you have the parameter, you have the coin flip, you can go to the second problem, which is what's the underlying path. And so you can use the backward forward procedure again to make the guesses, what's at each location, you re-estimate this, whether the coin is fair or biased. And then using the parameter, using the path again, you can update your initial probability, your transition probability, and your emission probability. And you just iterate this process. And by the time things are settled, you're done. So that's roughly how the third problem is solved. And there is no guarantee. You can imagine if you don't start correctly, you might get some wrong result. But so you have to restart a number of times. So that's kind of the idea to solve the third problem. And so you only have the string of coin flips, and you are trying to guess what's the coin used, and also you are trying to estimate all the parameters under the coin. In most of the situation in research, we're actually dealing with the third problem. We don't have the parameters ahead of time. We have to estimate the parameters and also make the paths prediction at the same time. Hidden Markov model has been used a lot in bioinformatics applications. So I want to show you a few examples. The first is gene prediction. When the human genome was first sequenced, scientists used hidden Markov model in order to predict genes in the genome. Because from existing knowledge of the genes, they have some idea what genes might look like. They say, well, the gene needs to start from, like usually, well, this is kind of a simple one, but the actual gene model could be more complicated. You might have, for a gene, you have a promoter, and then there's a transcription start site. And then you'll start to see exons and introns. So in this case, this is so this is the coding model for the coding region. This is the intergenic region. And this is the stop codon and the start codon in order. So you start from a gene. In the exons, start codon have every 3 amino acid codes for, every 3 nucleotide code for amino acid. And then you might have introns in the middle, and then another exon and an intron and another exon, and then it ends with stop codon and also the end of the exon, untranslated regions, and then you go to intergenic regions in the genome. And so these are the hidden states, actually a lot, more than 2, because there's promoter, there's exon, there's the first exon and the last exon, there's the middle exons, and also there are many, many introns. And then you have intergenic regions, which are in between genes. And then at every particular hidden states, you could say, well, because promoter, we know that there's CPG island, maybe there's like a CG rich region. And in the codon regions, you should not see stop codon until you're at the last exon. Otherwise, the gene will terminate early. And so you will have the probability of seeing particular nucleotide sequence. And the model can be trained with some basic knowledge of existing genes, but then after the genome sequence is sequenced, you can use that initial estimate to run through against the genome, identify some genes, and then update the parameters again and run it through again, and so on until it converges. Then you will get the parameters for predicting genes, but also annotated genes in the genome. You can use hidden Markov model for protein structure prediction. So here, the hidden states are these are secondary protein structure prediction. The hidden states are the secondary structures that are known to represent protein structure, which includes alpha helix, beta sheet, and the coil. So coil are you can see alpha helix is like this, sheets are like up and down, like a strand. And then coil is the spacer connecting them. And so they are, usually when you are in one secondary structure, it's more likely to stay in the same structure, but there is a small probability it will transition to the other two. And at each secondary structure, there is also the probability of emitting different amino acid sequences. For example, prolines it has a very rigid structure, so it's unlikely to really happen in alpha helix. It might happen in beta sheet when the sheets turn around, but it doesn't happen in the middle of a sheet or beta strand. And coil is much more flexible and so on. And so using the hidden Markov model, so the observation you have is a string of amino acid sequence you see on a particular protein, and you are trying to train a model including all the parameters in order to predict on this protein which location is a helix, which location is a beta strand or beta sheet, and which locations are the coils that connects them. Another example for using hidden Markov model is to predict the copy number variations in the genome. You can imagine this as either sequencing result or this is early day, say microarray result. You hybridize, in microarray days, you use some reference genome, which, across the genome, we should have two copies of chromosomes, but you use some, average genome as your control, and you use another, this new person's genome as whatever the condition you want to see, and you compare their coverage across the genome. Or from high throughput sequencing days, you can just imagine you calculate the read coverage across the chromosome of an individual. And you should expect this to be even, and this would be the diploid genome. But in some regions, you might see that suddenly the coverage become much, much lower, and other regions, it's much, much higher. Occasionally, you might see a little noise. This could be, sequencing or microarray, the probe is not working, or the sequencing result, that region, you just occasional high coverage, you may or may not have confidence to call it. But if you have, consecutive regions with lower coverage or higher coverage, you might be able to call this as a duplication or deletion in the genome, which has copy number changes. And you can imagine the hidden states are the diploid genome, which is probably majority of the regions. So that has a very, very strong initial probability and a strong transition probability to stay in the diploid genome, but occasionally you might see a deletion or a duplication. But in this case, you can see there's zero probability to go from a deletion directly to a duplication and vice versa. So you always go back to diploid before you go to the other branch, the other possibility. And the emission probability is, the probability of seeing this level of read coverage or microarray hybridization signals. Whereas deletion, you can see there's kind of a lower distribution, and duplication will be higher. And so you can use this to call the copy number variation regions across the genome of an individual. The reason we cover this particular lecture now after the hidden Markov, after the HistoMark ChIP-seq is hidden Markov model has been used to annotate regions in the genome. You remember there are different histomarks across the genome. Different histomarks like K4 trimethylation. Remember, that's kind of a promoter mark. K4 monomethylation, which marks enhancers. K27 acetylation, which marks active genes or active enhancers. There are also K27 trimethylation, which mark repressed regions, K9 trimethylation, which mark repetitive regions in the genome. And so imagine if across the genome, people have done the many different histomark ChIP-seq. By looking at all the data together, this is a work done by Manolis Kallis's lab at MIT. They can divide the genome into many different states. And so some states could be promoters. Some region could be exons. It's like it is similar to a gene prediction or a genome annotation. This region is the enhancer. This region is a suppressor, that region is a repeat region, that region is exon, that region is a promoter, and so on. But instead of using genomic DNA sequence as the input data, it's using all the histomark data across. So in this study, the discrete time is 200 base pair region in the genome. They divided the genome into 200 base pair bins, and at every location, it looks at the histomark signal. What's the observation is, what's the K4 trimethylation signal, K27 acetylation signal, what's the K79 methylation signal, K4 monomethylation signal, and so on. And based on all these observations, it makes a best guess that, oh, this region is a promoter. And we know if this is a promoter, then the region next to it is likely to be a first exon of a gene. And so there's a transition probability there. The hidden states are the genome annotation or the states of the genome. And so Chrome-HMM is the method that can predict the chromatin states or chromatin domains based on the histomark data. Another application which you will see in homework 4 is to predict the chromatin topology. So in addition to annotating which region of the genome has promoters and enhancers, in the next lecture, you will see that the genome very often has these topologically associating domains. And so sometimes within a domain, there are stronger interactions. This particular region of the genome interact with another region of the genome, even though they are further away, say 100 kb away, there's kind of interactions. And so, and they dictate, how often things interact with each other. And what you would see is, for example, in this region, this is one domain. And so a lot of interactions happens within here. And so if we look at, this region, so there are assays to detect how things interact. And so this is calculating whether that interaction is biased for one side or the other. If you have even interaction, so this actually is one domain. And at the beginning of the domain, if you look at how things interact, you almost never see this region interacting with the domain before, but you see interactions with everything after. So there's like a very strong bias towards interaction to things after. But if you reach the middle of this domain, at this point, there is an even chance of interacting with both the sequence before and the sequence after, then the signal is kind of even. It's like to 0. But then if you keep going in here, these regions have a very strong propensity to interact within its own domain, which means it's interacting with sequence before, but it doesn't interact with anything afterwards. Then there is a very strong bias in here as well. So based on the chromatin interaction data, you will see that these type of interaction are suddenly biased towards interaction with things after or interactions with sequences before. And we can call these type of boundaries very clearly as a chromatin domain. And you can use this to identify chromatin topologically associating domains. And in the next lecture, you will learn more about higher order chromatin interaction. And you also use homework 4 to see how this is really predicted. And so in summary, you can see Markov chain and also especially hidden Markov chain are very, very useful. The models in a hidden Markov model includes the observations, which is the coin flip, the hidden states, which are the coins that you are using. And there's initial probability, which is the likelihood you start with something, the coin. Transition probability is the likelihood of changing between the coins, and emission probability is the likelihood of seeing the observation using the hidden states, under the hidden states. And there are 3 problems that we explain the solutions for. The first is, if the hidden Markov model parameters are already given, what is the probability of seeing a string of observations? And we can use either forward procedure or the backward procedure, and you should get the same results. The second problem is to infer the hidden states, knowing the parameters. And for that, what's the probability, what is the state at every location? And you can use either the forward, backward algorithm, which can give you a probability prediction at every location. But also Viterbi algorithm, which will give you the best path that maximize the overall string of observations. The third problem is harder because you only have the observations, but the parameter of the hidden Markov model is not given ahead of time. And we talk about similar to an expectation maximization approach, which is the Baum-Welsh approach. You randomly start somewhere, maybe use some reasonable, good sense to initialize the parameters. And then you use the parameters to guess the hidden path. And then once you make the hidden path guess, you update your model parameters and you iterate this process until you converge. Hidden Markov model has really been used in bioinformatics a lot. And you'll see that in the next lecture as well and in homework 4. Okay, that's all.